Let us start today with a problem. Suppose we have Alice and Bob. Now suppose that Alice wants to send a secret message to Bob, but she does not want her nosy boss to be able to read this message. Now suppose that Alice and Bob can only communicate through their work emails, which their boss has full access to. How can Alice come up with a secret code that she and Bob can use to send secret messages back and forth without their boss being able to find out the secret message, given that he can read all of their communications? Well, to solve this problem, I will need to tell you about group theory. And at first, this may seem a little bit technical, but I promise you it will be worth it at the end. So, what is group theory? Group theory, broadly speaking, is how we codify the idea of symmetry, or how we can move an object so that it stays the same. For example, consider a regular hexagon. We can rotate this object 60 degrees about its center and it will stay completely the same. Furthermore, we can flip this hexagon about a horizontal axis and it will look completely indistinguishable from the original. These are symmetries, and in some sense, these symmetries form a group. So what is a group? A group is a set G with a binary operation from G cross G to G. So what is a binary operation? A binary operation takes in two inputs from G and gives out another output in G. An example of this is multiplication. And throughout this video, when I say G multiplied with some other thing, I mean that we are applying this binary operation. So this set G has some rules. The first one is that there has to be an identity element, i.e., there has to be some element such that when we multiply it by an element of the group G, we get that same element back. The next rule is that for any element of G, there has to exist a unique inverse element, such that when we multiply them together, we get back the identity element, which gives us this property. Finally, this group has to be associative, or the grouping of terms in a multiplication doesn't matter. There is a fourth rule, but this is covered by us defining the binary operation. This fourth rule is that G has to be closed, or that when we multiply two elements of G, we get another element of G. So, returning to our hexagon example, we see that this definition kind of makes sense. We want there to be an element which does nothing, and we also want there to be, for every action, we want there to be a unique action which undoes that action. And we also want it to be true that however we may group the rotations or reflections of the hexagon, the final result will not matter on depending on the order in which we group them. So now let us define a hexagon group. Let us call alpha the element which corresponds to rotating the hexagon 60 degrees. And let us say beta is the element which corresponds to flipping the hexagon by a horizontal axis. These two elements, along with the identity element, generate the group, and I will show that group here. This hexagon group is called the 12th dihedral group, or D12, and we denote it as such. But there are many other dihedral groups, such as D4 and D8, which is the symmetries of a square. There are also other groups, such as S6, which is the sixth symmetrical group, or the group of permutations of 6 elements. But there are many others, in fact, infinitely more groups. So, given that there are so many groups, how can we tell if two groups, G and H, are actually equal and they're just in disguise? Well, to do this, we define a function from G to H, and this function will map elements of G to H. Since G and H are really the same group, it makes sense that they are the same size, and therefore it also makes sense that our function is one-to-one. In other words, when this is true, we say that f is bijective. Furthermore, we also want it to be true that if we multiply two elements in G and then apply f, it should be the same as first applying f individually to the two elements of G and then multiplying them together. This is called the homomorphism property. If these two properties are true, we say that f is an isomorphism and G is isomorphic to H. So when we have a group G, there also can exist groups which are subsets of that group G. When this is true, we call that a subgroup, and we denote it by a less than or equal to sign, but it actually means that it's a subgroup. So, for example, we have that the integers under addition are a subgroup of the rationals under addition, which are a subgroup of the reals, which are a subgroup of the complex numbers. So this kind of begs the question, how can we divide up a group? How can we split it into sections that come together to form the group again? And the answer to this is a coset. So what is a coset? A coset is just a element of G which is multiplied by every element of H. So it's just a set, say H is like H1, H2, H3. It's just a set G times H1, G times H2, G times H3, and so on. And it turns out that the set of all cosets partitions G. So when we say partitions G, we mean that each coset is disjoint to other cosets and their union is equal to G. So how do we know this is true? Well, we can first show that all the cosets are disjoint. So suppose they're not disjoint, and there exists some element x which is in the intersection of these two cosets, G1H and G2H. So by the way we have defined a coset, we can express G, an element of X is an element of G1H and it's an element of G2H, and we can express it like this. And rearranging this a little bit gives us that G1 is equal to G2 times H2 H1 inverse. And when we multiply by some random element of H, and every element of H, we get that G1H is G2H2 H1 inverse and H. And then we get G1H is a subset of G2H because H2, H1 inverse, and H are in fact elements of H. And they multiply to be an element of H. Using similar logic, but in reverse, we can also determine that G2H is a subset of G1 big H. And then this leads us to the conclusion that G1H is actually equal to G2H, which means that if these two cosets have an intersection, then they must be the same, and if they're not the same, then they must be disjoint. And the next thing to show is that the union of all the cosets gives us G. But this isn't too hard to see by just considering how we've defined a coset. When we take the union, we already have all the elements of G by just considering G times E, which is the identity, which is included in H because it's a group. And we can also get all the elements of G multiplied by the elements of H, which all form the bigger group G. So now we can show that all the cosets have the same size. And we do this by defining a function phi from G1H to G2H, and we just map for every H, G1H to G2H. And it's not too difficult to see that this is one-to-one and a bijection, which must mean that these two cosets have the same size. So why did we do all this? What was the point of all of this? Well, the point of all this was to come up with a fundamental theorem in group theory which will help us solve the original problem. So what do we know? We know that the space of cosets partitions a group. All the cosets of H in G are the same size, and all the cosets of H in G are equal to the size of H. So when we think about this means that the size of G is equal to the number of cosets of H and G times the size of all of these cosets. And we can think about this for a second, and you can see that it makes sense. And when we simplify this a little bit, we can see that the order of G, which is just a fancy word for the size of G, is equal to the index of G and H, which is just a fancy term for the number of cosets of H in G, times the size of the cosets, which we just determined is equal to the size of H. And then this means that, in fact, if we have a subgroup of G, H, then it must divide, then its order must divide the order of G. And this is very important. So now I will talk about a theorem that you may have seen before. It is called in number theory, and it is called Fermat's little theorem. And it goes like this. So this theorem does have an inductive proof that does not use group theory, but its proof using group theory is extremely elegant, and you must see it. So how does it go? So we say that we know that z mod pz, which is just the integers modulo p, and this is a group if p is prime, and you can check this, and it is true. So since this is a group, we can consider the subgroup generated by A, and we'll call it H. And this consists of just 1, A to the 1, A to the 2, and at some point this will loop back around to 1. And then we say that and it will be true that if we raise the order of H is the number of times we have to multiply A so that it loops back around. So A to the H would A to the order of H would be 1. So we know by the theorem we just showed that since H is a subgroup of Z mod Pz, then the order of H divides the order of Z mod Pz, which is equal to P minus 1. So H times some number D equals P minus 1. So using this, we can get this chain. So A to the P minus 1 can be expressed as H times D, order of H times D, which can be expressed as A to the power of the order of H to the power of D, which is 1 to the D, which is 1 mod P, thereby proving this theorem. And this theorem does have a generalization, which is called the Euler-Fermat theorem, and the proof is quite similar to what we just showed, except when we consider the subgroup, when we consider the group, we just consider all elements that are coprime to n. So now we will return to our problem, and we can use these tools to figure out how we can encrypt a message without the boss finding out. So suppose that Bob chooses 2 primes, and for simplicity, let's just say that they're 5 and 7. So we let this be true. So we define n to be 5 times 7, and define a to be 5 minus 1 times 7 minus 1. And so next we choose a number e, which is between 1 and n, such that e and a are coprime. So in this example, we will choose e equals 11. So this number e and n will be our public key. So this information is public, E and N, and we can send this to the work email and the boss can see it. But we have to keep A private. Next, we need to choose a message. For now, we can just assume that our message is a number and they have some way of converting text to number. In this case, let the message be 4. So now to encrypt our message, we will take 4 to the power 11 mod 35. So the message to the power of E mod n. And this will be our encrypted message. And this would be 9 in this case. So we send this to Bob. And so Bob has selected all of these numbers. And when he did, he knew what 2 primes multiplied to n. And therefore he was able to figure out what A was. So now when Bob did this, he found some number D, which was the multiplicative inverse of the encryption key E. And what this means is that he just found some number D such that D times E is congruent to 1 mod A. So in this case, it would be D times 11 is congruent to 1 mod 24, and we get D is equal to 11. So in this case, the private key is equal to the public key. So now, to decrypt the message that Alice has sent using our encryption function, which outputted 9, he applies a decryption function by taking whatever came out of the encryption function and raising it to the power d. So in this case, we took 9 to the power d, or 9 to the power 11, which happened to be congruent to, which is congruent to 4 mod 35. And we notice that this is the original message. And this works for all messages. And this is happens to be true by using our generalized Euler-Fermat theorem from before. And you can think of it as an exercise to prove it. So although this example is quite simple, but when we use extremely large primes P and Q, it becomes almost impossible to be able to crack this code. If once we send n, we the boss would not be able to prime factorize an extremely large number, and even if he was, he would still have to be able to find the multiplicative inverse d to of the encryption key to actually be able to decode the message. And this makes this code extremely secure. And in fact, this encryption system is used in all of on all of the modern day internet. And it is what helps keep your money and you secure while online. So that is it for today. And until then, see you next time.